Alright, welcome to the NUPOC video study guide number 99. Let's take a look at some problems now that I'm calling geometry by calculus. And what I mean by that is just problems that ask us to use calculus to find things like area or volume or other properties that depend on geometry like center of mass or moment of inertia, right? And these are really great problems and they're really applicable to engineering, and honestly I'm surprised that for some reason I haven't done a problem like this yet. So let's start by using calculus to derive the area of a circle. And there's actually two approaches to doing this. One is a little bit more general, and the other one you kind of do some analysis up front and it makes the integral a little bit simpler. So let's take a look at the general method first. If I have a circle like this, I'm going to start by putting a little dot at the center there, and we want to integrate over this entire area, right? Well, first of all, if we have a circle, it makes a lot more sense to use polar coordinates instead of rectangular coordinates. If we use rectangular coordinates, we're going to be dealing with both x and y changing as we move over x, y will be changing, and we're going to have a square root in there and a squared term, right, because of the way a circle is defined in rectangular coordinates, so it's going to get really messy. But if we use polar coordinates, it's extremely simple. So using polar coordinates, right, I'm going to have a small, pointing out from the center, a differential radius, right? I'm going to call that dr, right? And I'm also going to have a differential angle theta, right? Because in polar coordinates we have r that points out from the center, and then theta, which is our angular displacement around the circle. So here we are going to have a small differential angle, and that is actually going to be r d theta, because as r increases, this little d theta will actually, this whole length here will actually increase, right? That's the arc length. The arc length along a circle, right, is the radius times the angle, right? So you can look that up elsewhere on some sort of geometry workbook or whatever. But if I have, a larger angle for the same radius, this arc length will be bigger, right? And for the same angle, the bigger I make that radius, right, that arc length is going to get wider because it expands away from the center. So anyways, how are we going to set up this integral? Well, first, what I'm going to do is I'm going to integrate from the center, right, all the way out to the perimeter of the circle to get that length, right? And so that integral would be 0 to, I'm going to call this distance capital R, so that's going to be 0 to capital R, right, dr. And that would give us that length. Now, once I've integrated out all the way to the perimeter here, now I'm going to take this whole line and I'm going to sweep it around the circle, just like a little radar sweep or something like that, and that will sweep out the entire area of the circle. So in order to do that, I'm going to integrate our differential angle, right, from 0 all the way to 2 pi, right? Because right here, like this angular displacement right here, right, again, it's dependent not only on the angle, if this is d theta, but also on the distance r from the center. So this is going to be r d theta. Now, and again from 0 to 2 pi. Now this r here, right, that needs to come out in front of the dr because this r is it's a function of dr, right? So we need to make sure that we integrate that with the dr portion of the integral. So this is going to become 0 to r, 0 to 2 pi, r dr d theta, and if we integrate the inner integral first, right, that's just 0 to r dr, well that just equals 1/2 capital R squared. So now if we do the outer integral, right, we can bring all this stuff out front because it's not dependent on theta. So we have 1/2 capital R squared, 0 to 2 pi d theta, well, that just equals 1/2 r squared times 2 pi, right? And so the 2 cancels with the 1/2, and we have the area equals pi r squared. Now the other way to think about this is to just find what this differential area is up front, and we can say that area equals the integral of that differential area, right? So what is that differential area, right? Well, it's if we took a little slice, right? If we took a little slice of that circle like this, it's like almost a little triangle, right? And we know that this distance is r, this distance is r, this distance is, that displacement is d theta, and this displacement right here, this is r d theta, right? And we know that the area of a triangle, since this is approximately a triangle, right? Because for a very small d theta, this length here is like almost straight, right? It's not going along much of the curve of the circle. So the area of this dA, I should put that after there, dA is very approximately just 1/2 base times height. So here's the base, here's the height, right? So it's 1/2 base times height. That's just r squared d theta. So now we can just go ahead and integrate this differential area from 0 to 2 pi, right? So we'll get area equals integral from 0 to 2 pi of 1/2 r squared d theta. Well, that's the same thing we had right here, right? We can pull this out front, and so we'll get, again, area equals pi r squared. So those are two ways, two different approaches, right, to get the area of a circle using calculus. And again, remember, when we draw out this differential area here, we are approximating as a triangle, right? And then just doing 1/2 base times height. And that's our differential area. And we integrate that differential area over the whole area, right? So thanks for watching, and as always, don't forget to click to subscribe so you don't miss out on upcoming videos.